In our code, we were limited in that every single string had to have the same length. But we can actually extend this implementation to variable length strings. So the idea with this is we first need to sort the strings by the length of the string. And then instead of just looking at all the strings, what we can do is just look at only those strings that we know are long enough. And since the string lengths are small numbers, or at least we're assuming that they are small numbers, the initial sort by length can actually be done using bucket sort, because we're just simply sorting by the length of the string and not the content of the strings. So then the words would be grouped up into buckets by length. So all the strings that have a certain length would be in one bucket, and all the strings of another length would be in another bucket, and so forth. We would then place those strings back into the original array. Then we just need to only look at those strings that have a character at a specific position. Here is our implementation of Radix Sort for sorting strings, except now we have variable length strings. So we'll take a look at our main method, and we'll see it's not too different from what we had before, except now we can have different length strings. So we have strings with 2 characters, some with 3, 4, 5. I think we go up to 7. Yeah, success is our largest one, so that goes up to 7. Now, when we call Radix Sort, what we're going to pass now is the length of the largest string. So in this case, we would pass 7. Now, everything else in main stays the same. We'll print the sorted strings when this is done. So now let's go inside the Radix Sort implementation, and we'll see some noticeable differences. So we're still going to have our array of buckets, where each bucket corresponds to an ASCII character. But we're also going to have the set of buckets that will allow us to organize the strings by their lengths. So we're going to have another set of buckets where each bucket corresponds to the number of characters. So we do max length plus 1. So that way we have a bucket, in this case, for strings with 7 characters, one with 6, some with 5, and so forth. There is one for 0, but we're not going to have a string of length 0. So we got to go from 1 to whatever the actual number of characters of the string is. So what we'll do here is we will initialize each bucket to be a new array list. So that way we will put all of our strings in the appropriate buckets there. And then we also have our buckets that we had from before for each ASCII character. So what we're going to do is we first put every single string in the appropriate bucket by length. So that's what's happening here in this for each loop. So for each string, we take the length of it and put it into the appropriate bucket. And then we're going to put those strings back into our array. So we're going to look at each string in all of the word list buckets. And for every string we find, we're going to add it to the string. So this is basically now going to be sorted by the number of characters in each string. So that's what this part is taking care of for us. Once we have that, then we get to the bulk of the actual algorithm. Now, the way this is working, we have this starting index. And the purpose of this is we're not going to sort all of the strings by the rightmost character. What we're going to do is we're going to, let me explain it this way. Imagine you have all your strings and they are left aligned. That's the way you should visualize it. So imagine all of your strings are left aligned. Now, some strings are longer than others. The ones that are shorter, imagine that there are like blank characters there in place of the extra characters. So like, for example, if you have a string of seven characters and a string of 2 characters, there are like 5 blank characters after the string with 2 characters. That's the way I would visualize this. So what we're doing here is we're only going to look at the strings that have a character at a specific spot. So like in our example here, we're first going to check all of the strings that have a character at position 6. Now in this case, if we take a look at our list here, we only have one word that has that one string, success. That's the only one that has a character at position 6. Okay? And then the next time we go through the loop, we're going to sort all the strings that have a character at position 5. So in this case, that's only going to be success because that's the only one that has a character in this position. And then we're going to go through it again, and we're going to sort all of the strings that have a character at position 4. So that would be success, I believe hello and water would be part of that. But that's what we're doing here, at least from a high level perspective. So we're only sorting those characters, those strings that have a character at a specific position. So once we have done that, so we're going to put them in the appropriate buckets based on that character. And then we're going to look at all the buckets and add them back into the array at the appropriate spot. So when we keep doing this over and over again, eventually we will get to the last iteration, which is looking at all of the strings with the character at position 0, which is the first character of every single string. So that's how we would sort all this. So try it out by hand a little bit at first. You can even add some lines of code here to see actually which words are being added to the buckets and what the array looks like when it's over with. But that's the way you should think of it. So we'll compile this. We get a couple of warnings. That's fine. That's just because of the typecasting that's going on here. Let's go ahead and run this. And we see that all of the strings are properly sorted by the first character, then the second character, and then we see here, like for example, with no and nope, they both start with NO, but the one with PE will come afterwards. So it is sorted properly in alphabetical order. So we see we have fog, go, hello, jump, and so forth. So this, sure enough, does properly sort a set of strings with different lengths. Now, what's the running time of this sort? Well, this version of Radix Sort is linear in the total number of characters in all of the strings. So this does pretty well under certain circumstances. It does well when the characters are from a very small alphabet, such as something like ASCII characters, and when the strings are very short or they're very similar to each other. Now, once this starts to kind of wane, where the average length starts getting very large, or the characters are starting to get very large, or the number of characters available, then the advantage of using Radix Sort does become minimized, and eventually it's just not useful at all.